this episode of the Cyclo Edition, the podcast for those looking to go above and beyond in their understanding of the organic literature. I'm Wesley Swords, and I'm joined today by Grace Lutovsky and Stephen Chapman. The paper we will be discussing today is titled CN Cross-Couplings for Site-Selective Late-Stage Diversification via Aryl Sulfonium Salts by the group of Tobias Ritter, who is a professor at the Max Planck Institute in Mulheim, Germany. His group focuses on synthetic organic and organometallic chemistry with interests in catalysis, medicine, and materials. This recent Jacq paper follows an earlier Nature paper from the Ritter group that details the initial studies of these aryl sulfonium salts. We will discuss these two papers from the group as well as a recent Engl paper they have published that describe how these sulfonium salts are a novel synthetic linchpin for highly selective para-CH activation and cross-coupling reactions.
Yeah, so this was actually really exciting for us because just with the process of starting this podcast, the Cyclo Edition, Matt, Wes, and I would sit down in like February and March and just kind of go over ideas of what we thought the podcast might look like. And in the process of doing this, we chose papers. And when this Nature paper came out, we were really excited about it and used it as one of our like practice sessions. So then we saw the Jacq's and the Engl paper come out like within the last month. We thought this would give us a chance to talk about the Nature paper, but then also talk about where they have gone since they published that. So we're really excited to talk about this today. So today, Wes and I are here to cover this paper. Unfortunately, Matt is on vacation right now, so we brought on Stephen Chapman, a fourth year in the UN group, to come help us out and discuss this paper.
Hi everyone, it's great to be here.
So today's paper comes from the group of Tobias Ritter. In this paper, he basically applies a functional group handle that he's developed for CH activation to CN cross-couplings, and in particular focuses on late-stage diversification with this handle. He first reported or disclosed this handle in a Nature letter at the beginning of this year, and in that case he showed the site-selective aromatic CH functionalization. And so in this case, he showed site-selective CH functionalization, and what was really interesting and impactful from that article was the selectivity that they got for Häring CH functionalization, in which case he was able to get greater than 99% selectivity for ortho substitution.
So following up on this, then more recently, earlier this month, he published two papers, one in Jacq's and one in Engl, and expanded the scope of what this functional group handle can do and the utility behind it. So today we're going to talk about kind of a mix of all three papers, the idea behind it, and what it has been applied to.
So as all of us have learned in our sophomore organic chemistry classes, there's a lot of functional handles like chlorides and bromides, and we also have triflates and different type of pseudohalides that we can use to be a handle for different cross-coupling reactions. And then we also have different nucleophilic substrates like boronic acids and boronic esters. So the Ritter group has developed an orthogonal approach with this Thianthrenium salt that is an electrophilic coupling partner to be compatible with pretty much any cross-coupling procedure that has been developed so far.
Part of the reason why they've been really investigating this is that selectivity that I mentioned a bit earlier, which is this idea that they get high selectivity for these compounds. And if you were to imagine doing bromination or borylation of simple arenes or late-stage complex arenes, you don't get nearly the selectivity that you might get there. In bromination or halogenation, the electronics of your substrate play the biggest role. So typically, if you want to get orthoselectivity, you have to have some sort of electron donating group. And if you want to have metaselectivity, then you go for some sort of electron withdrawing group. And in those cases, you may be able to then get push selectivity greater than 10 to 1. However, in many cases where you may have neutral rings or very little changes in the electron density, you get very poor selectivity for these sorts of processes.
And that's actually been an issue for me right now. So in the chemistry that I'm doing in the lab, I've been getting this horrible mixture of di and tetrabrominated products in one of the catalysts that I'm making, and it has been a pain to have to separate these. I have been having to go and separate these on a prep HPLC because they just are so similar on a column.
But yeah, Stephen, if you could selectively brominate one position or selectively install a functional group handle at one position, that would make your life easier, and that would probably make the life of many other chemists easier. So this reaction here aims to do that. And just to, I guess, put some numbers behind the selectivity that they're seeing versus what you might see with bromination or borylation is if they were to do a CH functionalization to add a bromine onto ethylbenzene, you would see 6-to-1 para to ortho selectivity. With installing a boronic ester on the same same substrate, you would get 1 to 2 para to meta selectivity. And so while you would still get these products, when you're looking at a larger scale process or late stage diversification, these selectivities aren't that great. And by doing the thianthrenation reaction, they are seeing over 500 to 1 para to ortho selectivity, which is huge.
Yeah, in these more recent papers, they even mention that they can't even isolate any of the other regioisomers that you might get out of these reactions. So they also mention that there have been a few cases in which you can get selective CH functionalization without the need of a directing group. The one example that they provide is a paraselective TEDA ylation of an Häring group. So that's just the addition of TEDA to, they show fluorobenzene. In that case, they're able to get selectivities of greater than 99 to 1. However, the handle that you now have, the TEDA group, does not give you any reactivity in cross-coupling reactions. And so the big selling point of the Nature paper that Tobias put out in March was that they're able to not only have this high selectivity, but now you have a very versatile and very reactive handle to then do further cross-coupling reactions.
Another way to access some of these similar molecules is to do a direct CH activation. So directly coupling your substrate with, in this case, a aryl CH bond. And this has been developed more recently. There's a lot of methods to do this, but a lot of those methods require either a directing group. So typically these directing groups are on the substrate and they will bind to the metal in a certain conformation to selectively add to a certain position.
So one of the best examples of this is when you have a phenylpyridine and you use some type of rhodium catalyzed reaction to do a selective CH functionalization to the ortho position. So nitrogen on the pyridine is able to coordinate with the metal center, and then your selective CH functionalization happens with excellent selectivity right there at that ortho position.
These directing groups have been very useful for running these selective CH activation reactions. However, the main limitation of these directing groups is the fact that they're typically difficult to remove. Recently, there's been a big push to kind of design traceless directing groups that can be removed from the reaction afterwards, such that you get the products you want without needing to have some sort of selective functionalization that you may not want in your final product. Ritter argues, as well as has been kind of argued by others, if we can just find methods that are selective to do cross-coupling reactions without the need for directing groups, that could be also very useful down the line to get a late-stage addition.
And I would actually argue that getting selective para-CH functionalization using a directing group is probably one of the hardest ways to do that, just because it's so far away from the functionality that you're relying on in the substrate in order to access that para position.
So in the Nature paper they published back in March, they discussed the idea behind their thianthrenation reaction, and they wanted to develop a highly selective CH functionalization reaction. So from there they started looking at how could you introduce a functional group handle that would be highly selective for the para position. Like, what characteristics does it need to have? So thinking about the design of this reaction, they actually published a paper earlier this year in Angew that was not selective, and so that gave them all of the constitutional isomers that they desired. And with that reaction, they noticed that it had an early transition state. So the transition state of the reaction looked more like the starting materials than the products did.
What that basically removes is the electronic bias, and in some cases even the steric bias of your reagents. And so when you're thinking about forming the carbon functional group bond, you end up not worrying so much about those sorts of biases in the reaction. Therefore, you can get para, meta, and ortho selectivity. To show that they had this early transition state, they used what's called a Hammett analysis, and in which you look at how the functional groups on your substrate or on the reactant that you're looking at change the rates of the reaction that you're running in. So you compare a base rate, which is typically the functional group being hydrogen, to more electron donating and electron withdrawing groups, and you compare the two rates. And then you can plot that ratio against some things that are called Hammett values, which have been determined for a control reaction. That control reaction in many cases is the deprotonation of benzoic acid. And if you're looking at other things, there are different control reactions for the different reactions you're looking at. And so what they found was, for this case where they were not getting selectivity in their reaction, they found that the slope of this Hammett plot was close to 0, which suggests that the rates for electron withdrawing groups and electron donating groups were about the same. And therefore, the rate for substitution for ortho, para, and meta positions would be about the same. In the case of trying to then generate a selective reaction, what they postulate is that what you really want is a very large slope of your Hammett plot, which suggests that the functional groups have a large significance on the rate of the reaction. So now your transition state looks very much more like your products, and therefore the electronic factors of the reaction are going to play a larger role in determining your selectivity. And so when they were looking for a new functional group handle to use, they came across papers from the 1970s that looked at thianthrocene, and when added to a aryl group, a thianthrenium cation would be generated. And what they found, just doing a simple Hammett analysis for this substrate, was that they got a very late transition state with a very large Hammett slope.
So that original report in the 1970s that described this thianthrocene being used actually shows the addition of the thianthrenium perchlorate radical cation that's able to add into a variety of arenes. So one thing to note is that these thianthrenium perchlorates, they actually report are explosive, and they report in their initial paper that they had a batch of the perchlorate salt actually explode while they were drying it and transferring it to a reaction. And so that was one obvious drawback for using these perchlorate salts. However, the thianthreniums were able to easily add into electron-rich arenes, but once they used benzene or any electron-poor arenes, they found that this thianthrenium radical cation wouldn't add into the substrate. However, in these original papers, they show that you can do this addition to the arenes, but then they never show any further reaction development from the system. So they don't show any type of cross-coupling or any type of derivatization from these aryl thianthrenium compounds.
So the major advance that this Nature paper showed was that the thianthronation of these arenes is highly selective, as well as showing that the thianthrene is basically an orthogonal pseudohalide that can be used in a large range of cross-coupling reactions. In the Nature paper, they focused mainly on cross-couplings that were run by palladium, your standard kind of cross-couplings that you'd expect there, as well as some copper-catalyzed photochemical reactions. And in all of those cases, they were able to get really, really good carbon-carbon bond formation reactions. And so in a two-step process that's highly selective for para functionalization in most of the cases, you're able to do a CH activation to then form a new carbon-carbon bond.
So in general, orthogonality is being able to independently functionalize one functional group handle over another. And where you might have seen this previously is with nitrogen protecting groups, or protecting groups in general. But specifically with nitrogen protecting groups, there are many methods to cleave a Bach protecting group over a tosyl protecting group, or vice versa. And so in this case, they show in figure 3b of the Nature paper that if they have the thianthrenium BF4 salt and a triflate in their molecule or a bromide, they can selectively couple to the thianthrenium salt over these other functional group handles.
So overall, this Nature paper kind of was really exciting when it came out in March. It was very interesting to see basically what is a new pseudohalide functional group handle to drive really selective reactions. And so earlier this month, when we saw that a new Jacq paper and Angew paper were published by the group that showed further application of the thianthrenium salts to organic synthesis, we really thought it'd be a fun topic to cover. And so now we'll go through the Jacq's paper, which we really thought kind of was a nice advance of the use of this functional group.
So as we transition from this Nature paper to the Jacq's paper, one of the reasons I really liked this new Jacq's paper that was just released is because they start to show a lot more diversity in the cross-coupling reactions that they're able to do. So the Nature paper shows all the CC coupling reactions that you would expect with like palladium-type couplings, but this new Jacq's paper is showing C-in cross-couplings. And this is obviously an important problem. C-in bond formation, definitely in a selective way, is something that is still a synthetic problem, and it's something that a lot of people are thinking about and trying to solve in creative new ways. I think the Ritter group really found a creative way to do this. So the Jacq's paper is going through the same Thianthrenium salt that they do in the Nature paper, and then they use a variety of different methods to couple on primary amines, secondary amines, and even some really complex in heterocycles. And doing these in heterocycle couplings is a challenging problem. And not only is it challenging, it's synthetically useful for pharmaceutical development and just to build up complex products in really quick ways.
If you would like more information on the background of carbon-nitrogen bond formation, we actually discussed this in 2 of our previous episodes. So in episode 5, we give an in-depth description of the importance of carbon-nitrogen bonds, and then in episode 1, we discuss many of the previous methods that have been published to form these bonds, such as the Buchwald-Hartwig cross-couplings and Ullmann and Chan-Lamb couplings. So if you're interested in learning more, please go watch our other episodes.
Focusing in on this Jacq paper, kind of split their scope into just kind of like 4 different sections, and so developed 4 methodologies for this chemistry. And one of the things I really enjoyed was the amount of detail that they gave on like how they kind of ran these reactions. And so like method A and B that they developed, which were for secondary amines and arylamines, amides, carbamates, or ureas, are based around kind of your standard palladium cross-coupling reactions. But for both of them, they had to develop kind of 2 different methods. With method A using kind of a palladium dimer and Rufos as its ligand, and kind of a mild base. They noted that they needed to use mild bases in these reactions because the Thianthrenium salts are sensitive to strong bases. In the paragraph where they discuss these methods, they give kind of a lot of like more detail on like what you can change in the reactions to kind of either help optimize your yield, or what you might be able to use as well that maintain reasonable yield without changing the reaction too much. So as we move through this paper, one of the major comments that the authors make here, as well as in the Engl and the Nature paper, is that there are actually 2 different derivatives of the Thianthrenium that they're able to use. One is just kind of your simple thianthrocene derived salt, as well as if you fluorinate the backbone, you're able to then access kind of different redox potentials for the Häring Thianthrenium salt. And what that allows them to do is have different rates of reaction for more electron withdrawing compounds. And so as they fluorinate the background, they say that they get better reactivity with certain substrates, and typically it's when they have more electron withdrawing functional groups.
So looking at the scope of this paper, they show, starting from an Häring substrate, that you can do the thianthronation reaction, and then couple that with some sort of amine, depending on the conditions that you use. So looking at their products, what really stands out in this scope is all of the complexity that they can tolerate. So one example that they highlight in the paper that is really impressive to us is the functionalization of strychnine. So they're able to selectively functionalize the para position of the Häring ring with this amination reaction. Other examples show functional group tolerance with esters, acetals, other nitrogen functional groups. They do this on sugar scaffolds, some steroid-like scaffolds. Basically, overall, they show that you can do this in a late-stage functionalization method, and that is compatible with many of these medicinally relevant compounds.
And you're right, Grace. The substrate scope is super impressive, and the selectivities that they get are amazing. One of my favorite in this scope is compound 13, and I like this substrate, although it's pretty simple because it shows the orthogonality of this cross-coupling handle. So they're able to add this complex in heterocycle in the presence of another bromine handle.
And another thing that substrate shows is you can do this on a more hindered position. So even though you're adding on the large Thianthrenium salt, you can do this ortho to a methyl group. So more hindered positions are accessible.
Moving forward from the development of this CN coupling reaction, the Ritter group has also developed a method to do late-stage trifluoromethylation on arenes as well, using these similar methods. In this Jacq paper, they developed 2 different styles of copper-catalyzed photoredox reactions. And so in this next paper, the trifluoromethylation paper, which they just published in Engl, they apply this copper photochemistry and actually kind of go into the mechanism of how this copper photochemistry works for their thianthrenium salts.
So over the course of these 3 papers that they've published all within the last year, they're really highlighting this thianthrenium as an important synthetic linchpin that is going to be used as an orthogonal functional group handle for both academic use and possibly for industry use as well.
Something that we failed to mention so far is that the Ritter group actually published a YouTube video that goes through the design of this reaction and how you would use it in your own lab. And so they're really focusing on how to implement this in either the academic setting or the industrial setting, and how to integrate this into your own chemistry that you are doing.
And that's our show. Thanks for tuning in to this episode of the Cyclo Edition. For more information on the papers discussed, we have included a selection of the resources we used in our research at the end of the YouTube video. This was our take on a very interesting paper, and we would love to continue the conversation with you. Please comment below the YouTube video and reach out on social media. You can follow the Cyclo Edition on Twitter, where we will post updates about our next episode. You can find the Cyclo Edition wherever you listen to podcasts and on YouTube. If you enjoyed this episode, please like and subscribe. We will provide the paper we will be discussing during the next episode in the description of this podcast, as well as on social media a few days before the next episode is released.